Yeah, okay.
Okay, nice, perfect. Then welcome to the Rising Star Symposium on Cyber-Physical Systems, Security, Resilience, and Privacy. Today's talk will be given by Sri, and Sri is a postdoc at the University of Pennsylvania, and he received his PhD last year from Uppsala University on automatic control. In his research, he's working on secure control systems, scalable control, dissipative systems, and adaptive control. And now we're looking forward to your talk.
Thank you very much. So my talk is going to be, as Sebastian said, on the analysis on design of secure control. So it's kind of my work that I have been doing in my PhD and in my postdoc. So as Sebastian said, I did my PhD in Uppsala, and my postdoc is between KTH in Sweden and UPenn in Philadelphia, and I'm primarily funded by the Swedish Research Council. So in this talk, I'm going to practically motivate the problem that I study, uh, and then give some analysis tools for the problem, and provide an outline of the design method. So traditionally, the problem of security comes from power grids. So in a power grid, for example, if you have the physical measurements of the power, so in a large power grid, you measure the voltages and the flow in some of the buses, for example, and then there is a state estimator in the remote control unit, and the state estimator estimates the phase angles and voltages. And there is also a bad data detector. So this bad data detector for linear systems, you can think it as a Kalman innovation. So this signal is the prediction error essentially. So in a deterministic setup, if there is a difference between these two, if these two values, the observed value and the predicted value, then there is an alarm raised. And in a stochastic setting, when there is noise, this epsilon can be made higher to tune the false alarm rate, for example. Yeah. And the control center usually solves an optimal power flow problem. So, for example, if there are generators, so if there is some demand in the power grid, so certain buses demand certain powers, then we have to generate power from, for example, generators, so that this constraint is satisfied, right? So the power generated and the power demanded sum up. And then the power flow in each line is below a particular threshold so that you avoid heat losses. So these are the constraints that the optimal power flow problem has to satisfy, and the objective is to minimize the generation cost. Although you have to generate certain amount of power, each generator demands a cost to generate a particular amount of power. Yeah, so they have some cost, and usually the objective of the operator is to give set points to each of the generators so that the total cost is reduced. And in under some assumptions in a deterministic setting, you can pose this as a convex problem. So for any given demanded power and any given saturated power flow, this is a convex problem. It has a unique solution. But usually these control centers are remote. So they can be susceptible to data integrity attacks, and this has been proven before. For example, in this work around 2009, they showed that there is an attack policy which can go undetected by the bad data detector and can still cause some harm to the power grids. I'll put more emphasis on what I mean by harm here. So, in order to explain what these attacks can do on the system, I assume that there is an attack on the measured power. Okay, so to be more precise, I assume that the actual demanded power is under attack. So the power demanded that we receive at the control center is this value. Similarly, the generated power by each generator is also received by attacked. So when we received these attacked measurements, we can also again solve this convex problem and see a fake optimal control input in general. So the effects of such an attack is that if you solve the if you solve the optimal convex problem under these fake measurements, you will see that while doing a redispatch, while applying this attacked control input, if you apply this, you will see that you gain something. But in reality, since the demand has not actually changed, you will actually face a loss. What I mean is, in essence, that in a convex problem, because of fake measurements, you're moving away from the optima. And because of this, you will face losses. And if under these conditions, if the profile of the generator given is too low, so there is too less power, so the slack generator has to pick up all the load, then the slack generator might actually go into unsafe operating regions. Yeah. So what I try to say in this is that because control systems or cyber-physical systems also operate or manage critical infrastructures, there is financial and physical consequences for these attacks. So the message is to be proactive and protect the system from a control theoretic viewpoint. But you might also ask, what about IT security? So IT security is a bit different from control system security in the fact that IT security, for instance, they care more about data traffic, for example, rather than what the data packet actually carries, not more about the data packet itself. And for control system security, physics can help detect attacks. And this physics is not usually considered in IT security. And also, if you come more from a fault detection perspective or a control background, faults can occur randomly. They don't need to have a pattern, but attackers usually, in the worst case, have a strategic intention. So there are some differences here. What my main message is to have control system security as an additional layer on top of IT security. So it does not take away IT security; it just adds on it. And this control system security has been a very long-standing field. Around 2009 was the first paper, and this paper was the one that I talked about before from a power system point of view. This is a long-standing research field, depending on how you define long. And my research, in particular in this field, is as follows. So I have four main research areas that I work on, and to explain this, I'll use a very small toy example to make things much simpler. So I consider heating system, right? So where the objective is to maintain temperature in a room, and I have some wireless network in order to control the fan and the heaters, and it's controlled using a PID controller, and then there is a detector. And here, instead of cost in the power grid that I explained before, I have a performance signal, which is the temperature deviation from a given set point. Okay. So this is the setup that I have now. And first, I'm interested in security metrics. So security metrics is more like putting a number on a system. So given that, let's say you give me a system, give me a power grid, I tell you that this is alpha secure. So I want to put a number on the system, and usually these are called security metrics. So for example, I can talk about how much the performance loss worsens when there is attack, or if it's a very large system, I can talk about how the attack surfaces, like the likelihood of the attack surfaces increase as the system becomes larger, or I can also talk about such metrics in uncertain environments. So this is one line of research that I do. And another line of research that we are interested in is secure design. So where I use these metrics for design, to design optimal controllers, to design the threshold optimally. or also from a data-driven perspective. And the first two that I introduced is about attack mitigation. So there is no prevention mechanism. So another line of research that I'm interested in is on attack prevention, such as coding schemes. Coding schemes you can think about as low latency, low cost encryption kind of. That's attack prevention. Also, you can randomly switch the detection threshold so the adversary does not know what the threshold is in principle. And finally, I'm also interested in scalable security, so how these tools scale without losing accuracy. So as you can see, I'm interested in these four, but I'll not present all of my research in great detail. What I'll do is I'll just take you on a walk through these research areas that on some of the problems that I've worked on. So I start with the top left on security metrics, and now I introduce some math. So I consider this example, and let's just say that these systems are LTI. So I consider that there is an attacker on the actuator. The dynamics of the room is given by an LTI system where YP is the performance measure or the temperature deviation with the full order feedback controller and the detector. So you can think of this detector, for instance, as a Kalman filter where YR is the innovation. I also consider that we do not know this A matrix exactly. So there is some parametric uncertainty here. I represent parametric uncertainty in this way. Now there is only one input to the system, which is the control signal, and there is two outputs. One is the performance measure, and the other one is the detection measure. So you can write it as a closed loop like this. Yeah. Now, before I go any further, I want to say a couple of things. One is that here, to keep things very simple, I introduce uncertainty only in the matrix A. You can generalize it to B and C in my works. I have done it, but I'll not do that now. You can also generalize it to continuous time systems. You can also generalize it to sensor attacks. So when sensor and actuator attacks occur simultaneously, they are called covert attacks. I deal with them separately at the end of this presentation. Yeah, these are some remarks that I would like to make. Now, let's consider this system, this closed loop system, and let's ask the question about who is uncertain. So first, let's talk about what we mean by uncertainty a bit more clearly, and then we talk about who is uncertain. So in this system, if you consider this heating system, what I mean here is that the matrix can actually represent the thermal conductivity of the heater, right? So this thermal conductivity might not be exactly known. There is a variance around it. So I know that it lives within the bound, but I don't know the value of this exactly, although there is a current value. There is a truth, but you don't know the truth exactly. Now we can talk about game theoretic approaches. So we can consider a perfect player or here by player, I mean the adversary or the operator, is the one who knows this current value. This exact ground truth is known to him. And an imperfect player is the one who only knows this boundary but does not know the exact value. Now we can have a game theoretic setup where on the x-axis I plot the process knowledge of the operator. On the y-axis I have the adversary. So when I'm perfect, we as the operator are imperfect, we can consider a perfect adversary or an imperfect adversary. And the same, when we are perfect, we can consider a perfect adversary and an imperfect adversary. And in these setups, now we can talk about how to quantify security, how to put numbers on systems. Okay, now these have different, depending on what setup you take to solve your problem, they have different connotations, right? So for example, if you assume that both the adversary and the operator are perfect, then this is a realistic setup. So in principle, what you assume is that both have uncertainty, but just assume that I do not know the system and I know as much about the system as the adversary knows. So that's kind of the setup here. And an optimistic setup is that we both know everything perfectly, or the worst case setup. That's a bit. So what I want to say is that there are different connotations on what setup you adopt to solve the problem. In my work, I have dealt with all of this in principle, but I'll not go through all of them. First, I start with this perfect and perfect setup. So in the perfect and perfect setup, there is no uncertainty here. Okay. Now I talk about how to put numbers on systems. So the first thing that I want to discuss is that an operator is said to have good performance when the performance loss is low. So for instance, if you consider this example, when the performance deviation is low, then we are said to have good performance, and we can assume that the adversary actually aims at increasing this performance cost, right? I measure it using L2 just for mathematical convenience. We can also consider a detector, like a simple detector, which raises an alarm when the norm of the innovation goes above a particular value. And you can assume that the adversary exactly does the opposite of maintaining this level below the threshold. And this is what I mean by security metrics. This is the security metric I work with mostly, and I call it the output gain. And using dissipative systems, you can actually show dissipative systems in S procedure. You can actually show that this is equivalent to a convex STP, where the constraints resemble a generalized Ricardi equation, Ricardi inequality. So this is one case. Now we move on. I explain another case where there is an imperfect operator and a perfect adversary. So what I mean is that the operator is imperfect. So I, as the operator, have some uncertainty, but I assume a worst case adversary where he knows everything perfectly. Okay, now there is uncertainty in the picture. So since the adversary knows the exact value of the uncertainty, he or she can exactly solve this problem. So for any given true value of the uncertainty, he or she can exactly solve this problem, right? But this is random to me. I do not know this exact value. What I do know is that delta lives in a set, but that's all I know. What you can do in this case to assess security is that you can plot the density function and then take a measure of the probability density function as your security. For example, if you have a function like this, you can either take the mean. So we can solve this optimization problem for all values of delta by sampling the set. And given that this has a density function, you can either take the mean or the value at risk or the conditional value at risk. And this actually gives you a measure of security. So this kind of combines operator adversarial knowledge, security, and then risk metrics to give you a measure of security in some sense. So yeah, so this kind of also gives you a probabilistic security metric. So for those of you who don't know what value at risk and conditional value at risk are, var alpha is that the mass function, uh, it's the value of the loss of the impact metric, below which the mass is greater than 1 minus alpha, and the tail is just alpha, and the conditional value at risk is the mean of the tail in principle. Yeah, so this is the first line of research that I'm interested in. I also want to say that there are very nice relations between the metric that I study and the metric that is actually in the literature. So this is the metric that we introduce in the literature. There are also H infinity, as you can see. The difference between our metric and H infinity is that we do not necessarily constrain the input to be bounded. We only constrain YR to be bounded. We do not constrain the input to be bounded. Due to this, you can reveal structural limitations of your system for security. And there is also H minus, which is more from the fault detection, fault tolerant control. And they care more about YR. So in comparison, our metric cares about performance and detection. H infinity cares more about performance. To be more accurate, it cares about the worst case performance. H minus is more about detection, so it's about the least detectable signal. So there are some relations, but our metric combines detection and performance in a single way. And because of this, you can exploit the structural limitations. And so the value of this metric can actually be infinity. There are two sides of this coin, so to say. So if the value is infinity, you can actually identify the scenarios where your system is vulnerable, but also you cannot use this metric for design anymore. So you have to adapt the metrics in some sense. We do identify some of the scenarios where it does go infinity, and then we propose some alterations to adapt this metric. We also propose adaptations in different setups, this omniscient rational setup. Yeah. So this is one part of my work. And the second part of my work is on design. So let's keep the same setup that we had before, where we consider an omniscient adversary and a rational operator. So here, as I said before, K is the controller gain. And this value of the controller is known to the adversary again. And as I said before, if this is the output to output gain for a given value of delta, since delta is not known to me, this becomes a random variable. And you can assess the risk using conditional value at risk. You can assess it using any risk metric, but here I choose the conditional value at risk. So the problem that I actually want to solve is that I want to minimize the risk using the controller gain, and the loss function is the one that I showed you before. Yeah. So I am not going to talk a lot about how I exactly solve it, but I'm just going to give you an overview of how I solve it. So this X is actually non-convex in K. You can do some tricks and convexify it, but you get an upper bound. And then you have a continuous set. You can sample from the set and solve the problem empirically. So you get a empirically solved problem instead of, so we want to solve this, but we essentially solve this. But one thing that we do is that we give probabilistic guarantees. So for those of you who don't know probabilistic guarantees, it's like conformal prediction. From those of you who are from the machine learning community, it's more like conformal prediction, but I use a tool called scenario optimization, but there are some links between the two. So we introduce a term called probability of shortfall. So for example, if I design this controller using the sampled measurements, if I design the controller using the sampled measurements, let's say I have this probability that I will see an uncertainty for which the convex upper bound is greater than a predefined value. Then what I can essentially say is that this probability of shortfall is below epsilon. And this epsilon will be affected by how much you sample and the dimension of the decision variable. So this is like a certificate that you give after you solve the problem. Yeah. This is a very short numerical example on the results. So on the right, I plot the impact proxy, like the convex upper bound of the non-convex objective. And this is the true non-convex objective. And I plotted both for the controller that we design and the nominal controller. Here, the nominal controller is the one that discards all the uncertainty. Yeah. So if you do this, so if you consider risk metrics to solve the optimization problem, in principle, what you do is that you reduce uh, you reduce the median. So you push the mass towards zero, where zero is the nominal one, right? So if there is no attacks and no uncertainty, zero will be your optimal value. So you push the red towards the towards zero, which is good because you have the mass towards zero. But one thing that happens is that the tail value can be quite high. So what it means is that on average you will perform better, but there are high risk, low probable events which can take your loss quite high. So it's a choice that the operator has to make. And here, the metric is tight, like the impact proxy and the impact is tight, but it's tight on very trivial cases. So we do want to extend this to other classes of other upper bounds, not necessarily this. This is not the optimal relaxation per se. Yeah. And we also give a priori probabilistic guarantees. Yeah, so this is the paper that talks about conformal prediction and scenario optimization. Now, one thing that I want to emphasize is that I have talked about output to output gain, like the SDP that I showed you before. Uh, I have talked about this and used this in a couple of examples that I showed you until now, but I just want to emphasize that this output to output gain is actually it has quite nice properties. Yeah. So for instance, if this is the optimization problem that we have to solve, right? Like the one that I showed you before. So instead of only optimizing the feedback gain, I also optimize over the observer gain. Okay. Let's say that this is the problem. Now, let's introduce some notation of the transfer function from the attack input to the performance measure and the residue measure. This should be YR, by the way, not YP. Let's introduce this notation. Actually, what happens is that if you minimize the output to output gain, what you're essentially doing is that you are pushing this ratio, like you are pushing the worst case ratio to be minimal. So what you're doing is that whenever the performance loss is quite high, so this is the singular values, right? So whenever the performance loss is quite high, what this optimization problem tries to do is that it also tries to increase the detection high. So whenever performance loss is high, it increases the detection. And whenever the performance loss is low, it just does not care, because I don't have to improve detection necessarily when already the performance loss is bad. I mean, I don't necessarily care. I mean, you can also see this in an example. So this is in the frequency domain, I plot the gains. The blue one is from our method, and the red ones are like H infinity and H minus, the standard in the literature. If you look at the low frequency, you can see that detection is improved in attack. So I just have to say that in this plot, you want the curve to be quite low. And in this plot, you want the plots to be quite high, like the values to be quite high, because this is about performance loss and this is about detection. So in the low frequency, you see that what we want actually happens, that the curve is pushed below and here the curve is pushed high. When you look at central frequencies, you can see that the performance loss is actually worse, but the detection also improves. You don't see it exactly at the same frequency because this is a non-convex problem and we solved it using bilinear alternating minimization. So we are not yet at the optimal solution, but this is analysis using the suboptimal solution. So if we do get the optimal, we believe that this peak could be here. And in high frequencies, the detection is actually worse, but you don't care because the performance is also actually not that high. So you don't have to increase detection. So what I want to say here is that output to output gain actually has some nice system theoretic properties in frequency domain. Yeah? But one thing that is quite important for such design problems is that they have to be scalable. Yeah. So for instance, in general, we obtain the value of the metric by solving an SDP. And this SDP does not necessarily scale well. For example, on the left, so forget about the algorithm one in red, just focus on the blue mosaic one. So this is the execution time and the accuracy of this SDP when you solve with the dense P, like a full P matrix. As you can see, the accuracy it's quite low. But when you solve the SDP with the diagonal P, the execution time is quite good, right? So if you solve it with a dense P, the execution time is worse. But with the diagonal P, it's actually quite good. And this was a work recently published from one of our postdocs in our group. So that begs the question, for what class of systems is using a diagonal P optimal when we solve this optimization problem? Yeah, that's a good question to ask. We do talk about that now. It's called scalable design or scalable allocation. So first I introduce a concept called positive systems. For those of who don't know, positive systems are a class of systems for which if you initialize the system in a positive initial state, and if the inputs are always positive, the states will always be positive. That's a positive system. And positive systems are quite well studied. They have many applications. Many physical systems are actually positive. But one of the nice properties of positive system is that they have a diagonal solution to the H infinity LMI. It's optimal to consider diagonal solutions. Yeah. So now this proves that they are scalable as well, right? Because you only have n elements to solve for instead of n into n plus 1 by 2. So can we inherit the scalable properties for our setup? The answer is yes, but in a very restricted setting. So let's say that you have a multi-agent system or like a power grid where each node represents a bus, or a set of drones where each node is a drone. And the performance of this multi-agent system is measured by the performance metric YP. And we assume that each node has a controller. So each bus can be controlled or each drone can be controlled. And each of these nodes has a controller of its own. And now we assume that one of this node is the controller node is under attack, like data injection attacks. Now, in order to counteract this, we also assume that one of the agents is monitored. So in a power grid, you just choose one of the nodes to monitor very closely. So you monitor its state's evolution and you also monitor its innovation signal quite closely. This system is positive if you assume that each of the agents has linear first order dynamics. There is also a related design problem as to if you have a very large system, how do you optimally select the monitor nodes? This is a related design problem as well. You can solve it as I explained it before. So this is a security metric for the single loop. You can also solve it for multi-agent systems where there are M attacks and there are M monitors. You can solve it with a dense P, but as I showed you before, you will have very poor accuracy. And this so what we do is that we actually, under some regularity assumptions, we show that instead of solving this optimization problem, you can solve the same SDP with the diagonal P. I'll explain what these regularity assumptions are later, like in the next slide. But I also want to say that if you look at in this problem, I don't constrain the attack to be bounded, but here I do constrain the attack to be L2 bounded, but this is to prove duality. Like this is very essential to prove duality with an SDP. You can remove this constraint, but the SDP value will be an upper bound instead of a lower, instead of being exact. So now what assumptions? The assumptions is this. We assume first order dynamics, and instead of attacks, if there is noise in the network, and if the network is quite robust to this noise, in principle, if the H infinity gain is quite small, then solving it with the diagonal SDP is optimal. That's the assumption. But you can also, if this assumption is not satisfied, you can always tune the controller gain to make it quite robust. Yeah. So that's what we show in this work. And we also show that the monitor's selection problem that I discussed before also becomes a mixed integer STP. So it is quite nice to have such properties. And this is a result that we have. So what we do, if you look at the bottom, it's the comparison of the computational time between solving with the full STP and solving with the diagonal STP. And on the top, we compare the output, the loss values. So the we get close to 10 power minus 6. So what we essentially mean is that we don't lose anything. It's just fine. You don't lose anything by considering a diagonal P is what I mean. Yeah. Uh, yeah. So another thing that we were interested in is that if you don't know, Sweden has this project called the NordSec project. So this project was about identifying power stations in Sweden, uh, which are quite which so they identified some of the some of the power stations and rebuilt them and essentially made the grid more resilient in some sense. Okay, so they identified this, and what so this was the project NordSec. Uh, this was by the Swedish Energy Grid Administration, which is Svenska Kraftnät. And then these guys later came and studied it from a system theoretic perspective. So these were power grid people. So what they did was they considered centrality measures of the grid, like how well connected the grid is, and came up with what are the grid points that are most vulnerable to natural disasters. So if there is a natural disaster, which points in the grid would be affected the most? Uh, Interestingly, the results of Svenska Kraftnät and these guys actually coincide. So like this, we didn't actually did what they are supposed to do to improve resilience. What we wanted to study is what are the nodes that are most attack, like like what are the most probable nodes to be attacked by an attacker. Yeah. And we consider a centrality measure called the CARDS centrality measure. It's I'm not going to explain in detail what this measure is, but it's similar to Google PageRank. Uh, so what this essentially means is that instead of solving output gain by an SDP, you can actually use card centrality measure. So if the output gain between a couple of nodes, so if you have one attack node and two monitor nodes, if the output gain between one pair is higher, then the corresponding card centrality measure will be lower. So this is like an intuitive way to guide designers to design. So instead of solving an SDP, they can talk more about centrality measures, which is more understandable for operators. Yeah, so this is one work that we are currently working on, and this is not yet published. Yeah, so this is my second part. So we introduce an output a metric called output gain and explain how to solve it for a design problem. We also showed that there were some frequency domain interpretations. Um, we also introduced a scalable approach to actually solve it, and we talked about positive systems. Positive systems actually also have, instead of considering L2 costs, you can actually also solve for L1 costs for positive system. But one caveat is that you can only talk about positive attack signals. We also currently work on relationship between security metrics and centrality measures. Yeah. So this was the second part. I'll just take 5 more minutes, if that's okay, to talk about the last part. Sorry for this presentation being too long. Um, it's about attack prevention. So until now, what I talked about is injection attacks, right? So someone injects attacks into the network, but I also talked only about attacks in the actuators. There is also another class of attacks called covert attacks, where so here an adversary injects attack both into the actuators and the sensors. And the covert attacks works like this. So if the adversary knows everything about the system, what he can do, he can inject an attack into the actuator, predict what the output is going to be, and cancel the effect of the attack exactly at the sensors. This is a covert attack, right? And this attack has been studied in the past, and the only way to stop such attacks is to distort the knowledge of the adversary. It's to introduce watermarks, essentially. That was our work. So there are lots of watermarks in the literature, like additive watermarks and moving target defenses, for example. We consider one particular type of watermark called multiplicative watermark. So multiplicative watermarks look like this, where each of the blocks are essentially LTI systems which are invertible. So when there are no attacks, there is actually no performance loss. So you can, for example, if you consider this to be a matrix, you can denote this as the inverse of this matrix. So now, usually what is done is that if you have such watermarks in the literature, what they do is that they introduce these blocks and then switch the values randomly. So you can just update it randomly. But what we wanted to study is that can we do it optimally in some sense? If you want to do it optimally, we assume that, let's say I update the parameters at this time step, I assume that the adversary knows the watermark parameters at the previous time step and then designs an attack with respect to those parameters. Yeah, uh, those parameters that he knows. This can be proposed as an optimization problem, just as I told you before. So the one in the red is the optimization problem the adversary solves. So he tries to increase the performance loss, respecting the system dynamics and stealth constraint of not increasing the Kalman innovation a lot. And then you can use the filter parameters to minimize this maximum. This is a nonlinear optimization problem. It's not even bilinear, but what we do is that we constrain the search space and solve it using exhaustive search. You actually gain a lot by doing optimal switching instead of random switching. So here I plot the cost, the output gain when you switch optimally and switch randomly. And here, as you can see, the cost clearly improves. You can also look at it from a trajectory point of view. So when there is no watermark, as you can see in the blue, the detection is very poor and the performance loss is also quite high. Whereas when you switch optimally, the detection improves faster than the performance, which is what you want. The detection improves faster than the performance loss is what you want, okay? So this is one kind of coding schemes that we study. There is also another coding scheme against zero dynamics attack, but I'm not going to go into that now. So in conclusion, what I am interested in general is about quantifying security and its relation to other metrics in the literature, and also how well they can inherit properties for scalable analysis, and also other design problems such as design. Optimal design of detectors and optimal design of observers, and also introducing architectures. Currently, we're working on introducing a linear program instead of a semi-definite program. And also, currently, I am personally interested in security via modular reduction. These are the references if you are interested. I just want to say finally that none of this work is just me. So I have very good collaborators, and these are all the collaborators that I want to say thank you to. And if you have any questions, I'll take them now.